Okay, good morning, afternoon, or evening, everybody. Welcome to the Guardian Monitoring Earth's Ionosphere for Natural Hazards and Near Real-Time Earth Data webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Savings Time, so we are going to go ahead and get started here. What I will do first is begin today's webinar with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, please enter those into the Q&A panel rather than the chat, and you should find that located on the right side of your screen. If you do not see that, click on the three dots in the lower right corner and you can select the Q&A panel. Okay, today's webinar is being recorded. The recording will be posted both to the NASA Earth Data website as well as to our NASA Earth Data YouTube channel within a week of completion, but likely much sooner than that. Excuse me. Once completed, I will send an email to all registrants with the recording links and also a link to the presentation slide deck used within today's event. As far as timing is concerned, today's webinar will be 1 hour long with 45 minutes allocated to the presentation and demonstration. A 15-minute Q&A period will follow, and depending on the volume of questions we receive, we may extend the Q&A session an additional 15 minutes from end time, but we will have a hard cutoff of 3:15 p.m. During today's webinar, we will have one speaker and two Q&A panelists. Our speaker for this afternoon is Dr. Siddharth Krishnamurthy. He is a research technologist within the Ionospheric and Atmospheric Remote Sensing Group at NASA's Jet Propulsion Laboratory. He will begin today's webinar with background information regarding the ionosphere and natural hazard monitoring. From there, he will provide an introduction to Guardian, its architecture, and key capabilities for ionospheric monitoring. After this, we will then transition to a live demonstration with several use case examples, and then a short discussion about AI-based automatic detection for ionospheric disturbances. We will then wrap up with information about Guardian's future direction. Our two primary Q&A panelists this afternoon are Dr. Leo Martir, who is a research technologist within the Ionospheric and Atmospheric Remote Sensing Group at NASA's JPL, and Dr. Attila Komjathi, who is the group supervisor within the Near Earth Tracking Systems Group, also at JPL. They will be available to address your questions within the Q&A as we go through this afternoon's webinar content, and also will be available at the end of the webinar during the Q&A session. We also have Dr. Patrick Michael on deck during the Q&A session. He is the NASA Crustal Dynamics Data Information System, or CDDIS, manager, and can address any questions that you may have regarding CDDIS datasets, services, or tools. Once our speaker has finished with his presentation and live demonstrations, we will transition to our final optional polls and then jump directly into the Q&A session. And just a quick final note about the Q&A, we will try to answer all questions within the time allotted, but if we are not able to address your question during the Q&A session or the extended Q&A, our speakers will be able to follow up with you offline. With that, it is my pleasure to introduce this afternoon's speaker, Dr. Siddharth Krishnamurthy. And at this point, I'm going to stop sharing my screen and transition the presenter role so he can get started. Give me just one. Here we go.
Thank you, Jennifer. Can you see my screen?
Yes, I can. Thank you very much.
I'll go full screen here. All right. Still good?
Looks good.
Yes, that looks very good. Thank you.
Thank you. Thank you, Jennifer, and greetings, everyone, wherever you are. I saw some people saying hi from distant parts of the world, so welcome to the NASA Earth Data webinar. And before I begin, I just want to thank Jennifer and her team for really doing all the legwork, helping set this up. This has been great. I'm Siddharth Krishnamurthy. I'm a research technologist at the NASA Jet Propulsion Laboratory, and I'm going to talk to you today about a system called Guardian, which is a near real-time monitor for the Earth's ionosphere, and our intention is to use it to monitor natural hazards on Earth through the ionosphere. As mentioned before, joining me today are two key team members of the Guardian team, Leo Martir and Attila Komjathi. who are both at NASA JPL, and they'll be helping with Q&A as I go along and Q&A at the end of this talk. So keeping in theme with the natural hazard warning framework that I'm going to discuss today, the US Federal Emergency Management Agency, FEMA, uh, coincidentally, by a pure coincidence, decided to conduct a emergency warning exercise exactly in the middle of this talk. So if you're in the US and your phone is not in airplane mode, you might receive a message from them about 10 minutes in. And so if you see me startled in about 10 minutes, you should know that it's FEMA, not me. And it's just a funny coincidence. It almost felt like they, got the memo about this talk or something. So having said that, let me recognize the team that makes up Guardian. So it's definitely a team effort, and there are several individuals, both at NASA JPL and a couple at Oregon State University, who have contributed to this talk. So I do want to recognize their contributions to the material in this talk. So I'm going to go into my outline, but before I do that, I just want to take some space to recognize the fact that we'll be talking today about natural hazards. In this field, natural hazards often produce signals that are scientifically important and scientifically fascinating. But it is important, I think, that we remember that these events have victims, and these events produce damage and cause grief. And so before I start, I just want to recognize the impact of these events on people around the world, and just let them know that, we have them in our thoughts as we talk about this today. So Jennifer's already shared a bit of my outline, but essentially I will, because this is a broad audience, I'll talk about the ionosphere a little bit and how we can use it for natural hazard monitoring. I'll introduce the Guardian architecture and how we can use that to do real-time monitoring. I'll show you some example use cases, and I'll also do a live demo, which, fingers crossed for live demos here. And I'll talk about a very exciting new development that we've been working on, which is an AI-based automated detection of ionospheric disturbances. Given that we want to use it as a hazard early warning system, this is an exciting new direction that we're taking this work in. And I'll conclude the talk by telling you where we're going in the future. And if you find yourself interested in contributing or taking this work further, please be sure to contact us. All right, having said that, a little bit of background about the Earth's ionosphere. So it is created by ionizing solar radiation. So when sunlight interacts with the Earth's atmosphere that's otherwise mostly neutral, it ionizes that atmosphere, creating the ionosphere, which lasts from about 60 kilometers to approximately 1,000 kilometers. The ionosphere also has layers within itself. It's considered a thinly ionized plasma, but it's still very electron rich. So it has about 10 to the 12 electrons per meter cube. The peak ionization happens in what is called the F layer at about 350 kilometers altitude above the Earth. Because of the Earth's magnetic field, the plasma is also magnetized, and it's dispersive, meaning that when radio waves pass through the plasma, notably those transmitted by satellites to receivers on the ground, those radio waves experience a phase delay that is proportional to the electron density and dependent on the frequency of the radio wave. Now, because this is frequency dependent and density dependent, if you're able to measure this phase at different frequencies, I'll show you in the next slide, you can actually use these changes in phase to infer changes in ionospheric density. And this is where the hazard warning part of this comes in. Events in space like solar storms, geomagnetic storms, but also natural hazards like tsunamis, earthquakes, volcanoes, meteor impacts, etc., generate atmospheric waves. So what happens, especially on the ground, is if you have an earthquake or a volcanic eruption or a tsunami, you'll produce these atmospheric waves that will then mechanically couple with the ionosphere and produce changes in ionospheric electron density. Now, as I said before, because the phase delays in these radio waves are dependent on this electron density, if you have a global navigation satellite, for instance, which is used for positioning otherwise, it's transmitting signals on the L band, which is about a couple gigahertz, to a receiver on the ground, then along this line of sight, if it passes through any of these fluctuations, you will experience phase delays. We measure this electron density in what is called total electron content, which is the integrated electron density along this line of sight. It's measured in electrons per meter square. It's an integrated quantity, but it's often reported in TEC units, so TECU or TEC units, and one TEC unit is 10 to the 16 electrons per meter square. So the so this formula here is what relates the phase difference. So if you're measuring the phase at two different frequencies, you can difference them, and ignoring biases and higher order terms, that comes out proportional to the TEC, which, as I mentioned, is the integrated electron density along this line of sight. So if you measure the phase at two different frequencies, in principle, you can invert that for the electron density along the line of sight. So an example of that is in the aftermath of the tragic Tohoku Oki event down here at the bottom. You can see that there were thousands of GNSS receivers on the Japanese mainland island, and where we could invert these signals for electron density, and you see these ripples in the electron density propagating away from the earthquake and tsunami. So there's clearly evidence of these signatures being present in the ionosphere and being diagnosable from these GNSS satellites and links. So let's start here again then. So what I was saying here is that when hazards happen, when earthquakes, volcanic eruptions, or tsunamis happen, or space weather happens, it produces atmospheric fluctuations, and these go and affect the ionosphere. And because the density in the ionosphere is proportional to the kind of phase delay that it can cause, we can use this formula down here, which is to measure phase at two different frequencies and difference it, and we will find that it results in a term that's to first order proportional to the total electron content, ignoring biases and higher order terms. The total electron content is the integrated density from along this line of sight between a navigation satellite and a receiver on the bottom. So an example of that is in the aftermath of this Tohoku Oki earthquake, which was a tragic earthquake in 2011. What we found there was that using GNSS receivers on the Japanese islands, and there were thousands of them, we were able to create this movie, this image where you can clearly see fluctuations in the ionospheric density in the aftermath of the earthquake and the tsunami, and also coincident with the tsunami. So there's very clear evidence here of the fact that these perturbations exist in the ionosphere and that these can be inverted for using GNSS, global navigation satellite systems, and the whole network. So one of the main advantages of doing this is essentially the coverage that a system like this offers. And so the geometry of the problem is such that these GNSS satellites are typically in medium Earth orbit, so pretty far away. And because these ground stations can see these satellites pretty far away, you can actually diagnose a portion of the ionosphere that's very, very far away from the ground station. So a single ground-based GNSS station is usually able to capture signals up to 1,200 kilometers away. So you don't actually need to have a GNSS station that is close to where the event is happening to be able to see it. In particular, now in the last 10 to 15 years, there are very many new constellations that are coming up, different countries. So there are four constellations that we typically track in the Guardian system, but there are new constellations coming up, especially from India, for instance. And what that does is that, so here I show three of those constellations: GPS, GLONASS is the Russian one, and Galileo is the European one. And this is from a single receiver So imagine the receiver at the center of the circle, and this is your view of the sky. And if you track multiple GNSS constellations, you're basically able to cover the entire sky. So with a single ground station and multi-GNSS, you can look pretty far away, 1,200 kilometers away. You can cover the whole sky. And because you have so many different independent observers, you can use fairly simple signal processing methods to distinguish these signals. So you will see fluctuations happen, etc. But they may happen because of random reasons. But if they happen together in the same way over multiple different observers, you're actually able to have some confidence that this is something geophysical. And this is something that we'll come back to towards the end when I start talking about the AI-based detection. So that's a single receiver, but now there's also been a proliferation of a large number of receivers around the world. So there are many GNSS networks. I'm showing you one here, which is the International GNSS Services network. And as you can see, there's a fair amount of global coverage. And so imagine the sky being covered with these links all over the world. And so that gives you a lot of monitoring potential. So coverage is definitely a very, very big advantage of this kind of system. Now, traditionally, this has been done in a post-processing mode. So like for the last 15 to 20 years, as GNSS has proliferated, researchers have used these data, used these ionospheric data days to weeks to months after a big event happens. And so when such an event happens, people typically download these data and they become available the next day. And then they're able to actually, invert these signals to get the ionospheric state after the event. Now, this is not ideal for natural hazard warnings because if you want to warn someone of an occurring natural disaster, you want to reach them relatively soon, right? So you want, for instance, that text that a bunch of the people in America just got from FEMA, you sort of want that kind of a system saying, something is happening, look out for it. So this is where the real-time aspect comes in. So if an event happens, it takes about 8 to 40 minutes for those waves to reach the ionosphere. And the signal will register virtually immediately, right? But now it's a question of when the data reaches you. So traditionally, in a non-real-time setting, you would probably have to wait about a day to get these data. But with the real-time system, these systems are relaying this phase data from the satellites, this link data and the satellite position, essentially now, right? Like through a network with very low latency, and you're able to get it to a data center immediately versus getting it the next day. And now, if you are able to do some analysis on the signal, you can actually produce, warning and science based on that signal very, very quickly. And so in this regard, I want to mention the GDGPS, the Global Differential GPS network. This network is managed out of JPL. There are over 200 real-time sites that provide this data in near real time. And so this is what really enables the Guardian system to use these data in real time. So not only does this possess the traditional benefits, which is that you can install these for positioning and you can install these, say, along plate boundaries to monitor the motion of tectonic plates, etc. But then now you also have near real-time ionospheric monitoring, which can be then used for natural hazard early warning. So our Guardian system is essentially based on this kind of network, and we present today a near real-time ionospheric monitor for natural hazards in the Pacific Ocean. So just a little bit of overview about Guardian. First, what does it stand for? It stands for GNSS-based Upper Atmospheric Real-Time Disaster Alert and Information Network. Uh, it acquires GNSS phase and orbit data in near real time from the GDGPS network, as I mentioned. The GDGPS network is now supported by the NASA Science Mission Directorate's Earth Science Division. So this is really a key enabling feature of this technology that we have built the entire Guardian system on. So what it does is it will take data from this near real-time network uh, all the time, essentially, at high rate, at 1 hertz, and it combines these phase measurements at different frequencies to generate TEC. So that equation that you saw a few slides ago is basically what it's doing, except it's doing it in real time. One of the key things that we've done here is that we buffer these TEC data for a few minutes. And what that allows us to do is that it allows us to clean the signal and do quality checks on the signal while keeping the monitoring aspect of it near real time. A lot of the disasters that we're looking at are things that move slower than that time scale. So it helps us stay real time, but it allows us to use a lot many more signal processing techniques when we buffer this data just for a few minutes. So we perform analysis on this data and we output it to a web interface. And now these data are also available through the Crustal Dynamics Data Information System, CDDIS. It's updated every 5 minutes. And so the community can actually go look at these data and do their own analysis on it. So in principle, Guardian is doing what Iono people have done for a very long time, but the real secret sauce here is that we're doing this in real time. And that's actually easier said than done because the data are not perfect and it actually requires a fair amount of maneuvering and network to be able to do this and provide this service in near real time. So here's how Guardian is organized as a software system. So as I had mentioned, we take our data in from the GDGPS network, and we also take satellite positions. This all comes in at 1 hertz. We need two frequencies because in order to invert the TC. So if you recall that equation that I showed you, it needs phase measurements at two different frequencies. So we do need dual frequency data. We fill out the buffer. We fix a lot of the data issues when they happen. So things such as cycle slips and gaps in the data. So cycle slips look like discontinuous jumps when the receiver loses lock for a little bit. So these need to be fixed because they start looking like spurious signals. Now, no fixing is of course perfect, but we do manage to remove a lot of these data glitches. And once we do that, we compute the TEC, we compute what is called the ionospheric pierce point, which is essentially the point at which this link intersects the height of the ionosphere. And then we output it in real time for all GNSS links. So we have about 90 stations, mostly concentrated around the Pacific Ring of Fire, and you will see this when we do the live demo. But we have the capacity to expand this further. So the recent addition, of course, is that now in addition to going on the web, these data are also available for the community to download and analyze themselves. Now, we want Guardian to be a hazard warning system. So there's other parts to this picture that are equally important. And the part on the right-hand side is an area of active research. So we made the left-hand side operational and we're actively working on the right-hand side. And what the right-hand side involves is essentially looking at these data, looking at these TEC data and doing what Iono experts and humans typically do, which is to comb through this data and see if something is going on. So that's our anomaly detection block here, which may use deterministic or statistical methods to look at these time series and be able to spot if something is behaving anomalously. So this is the block that tells you, hey, something is not right in this area, something is going on. You human being should go check. And then the other half of this is the fact that you might want to be able to classify and invert the signal. So when you see a TEC profile, you might want to be able to look at it and be thinking about, hey, what caused this? Is this a volcanic eruption? Is this a tsunami? Is this an earthquake? What is the energy output of this event? So is this a big tsunami, a small tsunami? Is this a big volcanic eruption, a small one? Is it a big earthquake, a small earthquake? And so we also have inversion as part of our system that we're working on. And for tsunamis, we have a prototype that works for the Tohoku Oki case. But this is obviously a very challenging problem because every geophysical event is different. It expresses itself somewhat differently, and so you need large data sets and a whole lot of research to actually make this operational. So the eventual vision for this is for having these parts integrated into the data collection system so that eventually we can work in a place where a human being could be actually issued some data and then they could make the judgment to issue a natural hazard warning with very specific parameters and be able to issue a text such as the one that you just received from NOAA. So that's kind of the intention here with how Guardian is organized. Now, one of the important things that we have to do here is we have to make sure that the real-time processing, because the data does have glitches, is not introducing some errors, and you are seeing the same data that you would see if you did this analysis 5 days later with post-processed data. So what we've done here is we have taken the measurements from Guardian and we've compared them to post-processed data. And we've done this in a way where we took stations from near the equator. So this is Galapagos on the left-hand side, and we went all the way to Fairbanks in Alaska, which is a high latitude station. And we compared data from the Guardian stream to post-processed data across 4 different constellations. So the GREC is GPS, GLONASS, Galileo, and Baidu. So those 4 different constellations. And what we found is that this gray area is the background noise in the ionosphere. And what we find is that within that noise across the board, we're doing really well in terms of the real-time stream matching the post-processed stream. So you have an example here where you can see you can't actually make out a difference between the post-process and the real-time stream. And in our sort of worst link case, sometimes you have these few deviations in noisy data, but it's still more or less within the background noise. So we are confident that what we are seeing is what we would see if we did some post-processing on it. So let's also talk about coverage. So in 2022, we had a number of stations around the Pacific Ring of Fire. Now, if you put a station on every piece of land that you could find in the Pacific Ocean, you would be able to cover about 82% of the Pacific Ocean. And that's just a function of the fact that there's not a whole lot of land in the Pacific Ocean. So in 2022, we covered about 59% of that 82%. So the max we can go is 82%, and we were at about 60% of that. And we identified some areas of strategic importance. So you can see these gaps in Antarctica, Easter Island, Central America, and near Russia. And so in 2023, we added several more stations, and that coverage has now increased by 12 percentage points. And so now we're at about 70% of the max. And so we still identify some gaps in strategic areas, and we are constantly working to get these stations going and get the data coverage as we want. So the coverage is there, the real-time aspect of this is there, and so this system is pretty well poised to monitor the ionosphere in real time. So having said that, I now have a live demo. I'm hoping this goes well with our bandwidth issues. This is an R&D website, so we do have a limited capacity for handling traffic to this website. But Jennifer, can you confirm that you can see my browser?
Yes, I can.
Okay.
Thank you.
Excellent. All right, so this is the Guardian website. It's at guardian.jpl.nasa.gov. When you land here, you're given instructions on how to navigate, but essentially what you see is a map with a lot of colored lines. And these lines are the location of the links of various constellations. So GPS, GLONASS, Galileo, and Baidu. As I said, we track 4 different constellations. You will see these circles, which are earthquakes from the USGS. Occasionally, and I will show you a movie after this slide, after this demo, these are blue colored, and these are essentially earthquakes that the USGS thinks have the potential to become tsunamigenic. So these are not declarations that a tsunami is happening, but these are sort of watch out for this earthquake. So how you typically interact with this website is, say you see this big earthquake, you can zoom into that area and select that area, and it'll show you all the earthquakes and stations that are within your selected area. So for instance, today we have a magnitude 6.4 earthquake. You get some data about that earthquake, about its location and time. And as I had said, the ionosphere is created primarily through the action of the sun on the neutral atmosphere. And so solar illumination actually becomes pretty important for monitoring things in the ionosphere. And so we provide data on the relative position of the event with respect to the sun. So it looks like this event happened between sunset and sunrise. So it was at a time when the sun was not present. And so typically nighttime events don't produce a very high signal. So you need a pretty strong event for that to happen. The other thing we mention in this selection box in the parentheses you can see is H, L, or M, and it's color coded. And this is the background noise level of the data. So this is just giving you an idea of the kind of station that you're looking at. A recent addition that we've had to this web page, and this is again something that typically Iono experts, like people who've looked at this in post-processing will do all the time, is they will look at what links were active close to the event in a certain time period, and then start looking at those links. And so what we're trying to do is make that work a lot faster. So this website now also shows you stations stations that have links that were active within 2 hours of the event, uh, once it happened. And these are also organized as by distance. So these are satellites that were active within 2 hours of the event, within 1,000 kilometers, and these are all organized by distance. And so if you want to look at the station, you can go to the page, and it is a lot of data, so it takes a minute to load. You're also experiencing high traffic, I'm sure. So when you load this page, you see all the links that were available in the last 24 hours for this satellite. The ones marked in green are the ones that are active right now or were active in the last hour. But let's look at, say, a couple of links in the closest one. So C208M, R720, and GPS 76. So we can look at C20M. We can look at GPS 66. And we can look at, say, R720. So I'm showing you 3 different constellations, and here's the data from it. So now, again, if you're someone who looks at ionospheric data, this background noise is actually pretty important. So this is where this notification that this station is actually a medium noise level station is actually pretty important, because as you can see, the background noise is actually pretty high at the time of the event. So this is actually not particularly easy to conclude that, oh, this is an actual signal that's happening. So another thing people typically do in the Iono world is they will not rely on a single link or a single station. They'll look at a collection of stations in an area. So if you want to look at some other station, you can also look at that simultaneously. So for this station, say, for instance, we look at GPS 70, GPS 45, and GPS 79, which are the 3 closest links. And we see these data here too. So towards the beginning or the end of links, you do end up getting a lot of these cycle slips and jumps. And so when it passes through a filter, it produces these large overshoots. We work pretty hard to try and curb these. Of course, like some of them get through, and not all stations create data of the same quality. So to demonstrate that to you, uh, I'll show you another station that's not related to an earthquake, but this is what one might call a good station, because this is the station at the Goldstone Deep Space Network site, and as you can see, it's marked L, which is a low noise station, and we can show you some data from that station, and you can see that it looks a lot cleaner, right? So it has much less background noise, and visibly cleaner sites. So not all stations are created equal. And so, but what we're trying to do is we're trying to take the guesswork out of this analysis. And typically, this data, you would have to download receiver Rhinex files, do your own processing scripts, do your own plotting scripts, and then analyze this data. And now this whole process I just showed you in 1 minute, that you can actually do this. These data are also explorable, so you can actually play around with the axes. You can zoom in, zoom out, look at specific times of this area, and then you can also reset your view when you're done. You can select as many or as few of these links and be able to analyze all of that. We also on the website have archives for the last 2 days. We have a bunch of examples that we'll talk about. And we also produce analysis such as a global noise plot that allows us to global noise plot that I have a picture of, that you can see all the background noise from all the from a bunch of the stations around the world. So that's it for the live demo, and I will move back now to the slides. Are we good with the slide? You can see it?
Yes.
Okay.
Yes, I can see your slide that indicates Guardian live
Yes.
demo.
Thank you.
Okay.
Appreciate it. Okay. So now this is an example case. You can see it on the web page. So on the left here we have post-processed data. So these are data that we run through our global ionospheric model, which is global ionospheric map, which is a software at JPL that takes data and post-processes it. And you can see in this movie, this is in the aftermath of the Tonga eruption last year, January 15, 2022. And you can see this gap in the ionosphere occurring after the eruption, and then you can see these waves passing over Australia in the ionosphere. So this is very reminiscent of that Tohoku Oki video, but these are post-processed data, right? So great for scientific analysis, perhaps not as useful for early warning. But on the right-hand side here, we have the Guardian web page, right? And this is pretending this was noon UTC on the day of the Guardian of the Tonga eruption. And as I mentioned, sometimes you will see this blue circle earthquake, which means that the USGS thinks this could be potentially tsunamigenic. We see all the solar information. We check what the closest links are. So I'm cheating here a little bit because when I made this video, I already went through all the links and know which ones the signal is at, but you can actually explore every single one of them. So I'll show you some signals in this video here, and it'll be very apparent that something is going on at about 4:30, 4:15, 4:30 UTC. So the eruption happened at 4:15, and very shortly after that, the signals reached the ionosphere. And we looked at two different stations here, LAUT and FDNA, and multiple links across different constellations. And in both cases, you can see there's a very, very large TEC perturbation across several links that happens virtually simultaneously on two different stations over two different links, right? And I will show you here that you can also zoom into these data, and then you can see the fluctuations, and you can very clearly see that basically at about 4:22 the entire thing goes bonkers a little bit. And so you can definitely see that signal very clearly. So another, perhaps the best use case of Guardian is in tsunami warning, for instance. And we have an example case on the website for the Haida Gwaii tsunami. This was an earthquake, a 7.8 that happened in 2012. And it happened on the western coast of Canada. And we actually saw a tsunami hit Hawaii. And so if you look at the Mauna Kea station in Hawaii, specifically Mauna Kea GPS 48 link, you can see this very clear ionospheric signal of a tsunami passing through. So you can actually go to the website and play around with the data and be able to see this signal and for yourself as well. So another interesting use case that we've come up for Guardian is relies on the fact that the ionosphere is also affected by events in space. And so if there's a geomagnetic storm or a solar storm, there was one in 2017 around 7th and 8th of September. And typically how this manifests in ionospheric data is that the background noise of the TEC signal gets pretty high during these storm phases. So I show you two stations here. One is Fairbanks, which is a high latitude station, and one is Goldstone, which is a mid latitude station. I showed you Goldstone in the live demo. And what you can see very clearly here on the left is that there is a very large increase in the background variability of the TEC. If you take the standard deviation, it has a marked increase in the middle and it drops off at the ends when the storm is over. And the high latitude station is affected a lot more than the mid latitude station. And so this is pretty typical of what you see. The polar ionospheric effects are typically stronger during geomagnetic storms than in the mid and low latitudes, right? So what we did with that is that we thought this is a very good way to actually see the signatures of an ongoing solar or geomagnetic event on Guardian data. And so on the website now, we actually display noise levels at stations at different magnetic latitudes, along with two indices called the KP and the AP index, which NOAA uses to track solar activity and geomagnetic activity. And so one thing you can see here is when this jumps up, which is sort of a noisy period, uh, you start getting very checkered behavior in the noise here. And so the noise jumps up anytime this goes up. And so things show up pretty clearly in the ionosphere, and daily noise variability actually gets swamped out by background by forcings from solar and geomagnetic storms. So we have natural hazards, we have space events. So we're using Guardian right now to monitor a lot of these events. But an exciting development in the Guardian field is this AI-based automated detection. And so, as I mentioned, this is an important part because it's a lot of data for a single human being to comb through and find patterns, right? So what we're trying to do is we're trying to replicate what an ionospheric expert looking at this data would do. And so for our prototype, we have this thing called long short-term memory, LSTM, and it's a neural network. And the assumption is that this neural network is able to learn business as usual temporal dynamics of the TEC profile. So what it does is we feed it a bunch of data or a bunch of training data from quiet periods. We know these periods are quiet, and it sort of learns from there what a quiet period looks like, right? And so now you've done the training, but in the test period, you then supply it data as it's going in, and it's then able to start spotting anomalous behavior. So if the ionospheric behavior deviates from normal, it starts to flag anomalies. But I think a key thing about geophysical anomalies, because anomalies can happen because of a lot of things, as I just showed you, some of the data are noisy, there's cycle slips, it runs through a filter, things happen, right? But the key thing about a geophysical anomaly is that there will be several spatially separated but close together observers that will show the anomaly in a phase correlated manner, and they will all be close to each other in the same geographical region. So that's like a very important part of this whole process. So the phase synchrony and distance threshold is what checks if there are multiple links that are in the same area that are all showing anomalous behavior, and that's where we declare an ionospheric anomaly. So the challenge here is also doing this with real-time data, right? So post-process data tends to be a lot cleaner, so this works pretty well with post-process data, but to be able to handle some of the anomalies in real-time data is where the challenge is. So for our test case, we used the 2023 Turkey earthquake sequence. So these were two earthquakes, a daytime magnitude 7.5 and a nighttime magnitude 7.8. And so these are some plots from nearby seismometers. And this was a very big earthquake, very damaging, unfortunately, and had some pretty high acceleration of 0.6 to 0.75 G within about 100 kilometers. So we have these two earthquakes. We have a few real-time stations nearby that we fed the data to these stations from about 1st December to 31st of January, so 2 months before the earthquake. And we used clean data, so we used higher elevation data, and we only fed it clean data to give it a sense of, hey, this is what normal looks like. And then we fed it data from 1st to the 7th of February and asked it to see if it can spot anomalies. And we got some pretty interesting results here because this is the signature from the daytime magnitude 7.5 event, and the areas plotted in red are the automatic recognized anomalies. And this is on real-time data, by the way. So this is data that was processed directly by Guardian. So it has all the imperfections of a real-time stream, but it has all the urgency also of a real-time stream. So this could be, in principle, something that is actually operating as an engine on our data as we generate it. And what we see is that it was able to spot the anomaly on the daytime event pretty well. What was not spotted was the anomaly in the 7.8 nighttime event. And so because it occurred during nighttime, it produced much lower signal levels, which kind of got drowned out in the noise. So a human observer would be able to see it very clearly, but the machine learning algorithm wasn't able to see it. So there's clearly some research work to do there, but this is an encouraging sign that we're actually able to see this in the ionosphere. Now, as I mentioned, tsunamis are some of the best test cases or use cases for Guardian, but uh, but the but the presence of these anomalies for earthquakes actually gives us a good proof of life that this is actually working pretty well. So I'm coming towards the end of this talk, but what I want to leave you with is a few thoughts. So the system clearly has a lot of advantages, right? So it's GNSS based, ionospheric based augmentations can really improve disaster warning time by several hours because of this enhanced field of view, because these stations can look really far away. We can operate them in near real time. They don't need to be close to where the event is happening, which means that you can also install them in places where you don't have to spend a lot of money maintaining them and spending money, keeping them up. And they also have multi-use functionality because you can use them for positioning, you can use them for tectonic plate motion, for instance, but then you can also use it for ionospheric monitoring. But it would be disingenuous of me to not tell you what the limitations of the system are. So ionospheric sensitivity, as is very clear now from the results I've shown, is very dependent on solar illumination. And so it does have diminished sensitivity at nighttime. So an event that happens at nighttime would need to be much larger for it to produce the same signal in the daytime, which is not to say they're not detectable, but the event needs to be larger. The signals take about 7 to 40 minutes to propagate to the ionosphere. So if you have a situation where you're trying to monitor for hazards near where the event is happening, and the event is fast moving in the way that the effects are felt before 7 to 40 minutes, you will not actually be able to see it in the ionosphere in time. So that's just a physics of the problem. It just dictates that time span, and so that's definitely a limitation. And usually, because this is a remote sensing method and involves coupling between different media, the weakest detectable event is usually going to be smaller than a terrestrial sensor. So for instance, for earthquakes, seismometers deployed around the world are able to detect, magnitude 1 to 2 earthquakes, right? But in the ionosphere, you would need something magnitude 6-ish or greater, for instance, for an earthquake to be able to see it. So the weakest detectable event in the ionosphere is usually smaller than terrestrial sensors. So the advantages are you'll get a lot more coverage, you'll get like a pretty fast response time for a low maintenance cost. The limitation is that your signal strength has some limitations based on the background conditions and also the travel time that it takes for the signal to get up there. So in conclusion, what I'd like to say is that Guardian is the first of its kind, state-of-the-art multi-GNSS near real-time ionospheric monitor. We are not aware of a system that does this anywhere else. The TC time series and analysis are now readily available, and people can explore it on the web page with just 3 minutes latency for over 90 stations and counting worldwide and across 4 different constellations. And it's a very scalable system. So with more resources, we are actually able to scale it up to many more stations around the world. We're also now making the data available through CDDIS, and the community can now look at this data and come up with its own algorithms for, event detection, for instance. And so the community is very welcome to look at these data and play with them. And so these ionospheric monitors could be used in the future to detect ionospheric signatures of various different events. So of course, as a warning system, there is a lot more work to do, but the signatures are all there in the ionosphere and Guardian is able to pick them up. And really speaking, natural hazard early warning is inherently multidisciplinary. So this is not intended as a replacement for any existing warning system, because they're all important measurements, because you need all these multi-modalities, multiple instruments to be able to issue an effective warning. It just brings certain advantages and could act as an augmentation to existing systems where they're not able to have coverage or where it can provide a little bit of extra time. So this is inherently a multidisciplinary field, and everyone's invited to participate. But it does offer an opportunity to expand and augment existing early warning systems, which really why we're doing this is with the hope that it will help save life and property. So with that thought, Our future directions are primarily aimed at anomaly recognition and classification algorithms, and also this data assimilation and source inversion. But we're also looking to expand this network beyond the Pacific Ring of Fire. And lastly, as just a sort of a programmatic note, Guardian will move to the NASA Earth Data Universe next year. So we will become as part of the web unification process, we will become a part of the NASA Earth data system. So that's an exciting new development that we will be fully part of the NASA umbrella next year, even though data is already currently available through CDDIS. So I just want to take a moment to acknowledge all our collaborators. And thank you very much for your attention. I apologize for the audio going out, but I hope after that we recovered pretty well. I'm very, very eager to see your questions. And I'm going to just hand this over to Jennifer now to moderate the Q&A session. Thank you.
Okay, thank you so much. So let's see here. We have quite a few questions. So I'm going to actually start with some of the questions that were not answered in the chat, and then we'll hop back down to the Q&A. Okay, we'll get to as many questions as we can, and for those questions that we're not able to answer, our speakers will be able to follow up with you offline. Okay, so let's see. The first question it's really more of a comment, but perhaps you can lend some additional feedback. I have accessed the website, the Guardian website, but there's no data available for example station DVAO.
Yeah. So what happens is, especially at a time like today, as I said, we're an R&D website, right? So we have limitations on how much traffic we can handle. So some days like today, when we have high traffic, the data will be slow to load, and so you might sometimes see that you come to the station and the data is loading, and you just happen to click on it exactly as the data were loading. So what I would recommend is if you maybe wait a few hours, let the traffic die down a little bit, and then try again, you will be able to see the data, I guarantee it. And
Okay.
eventually, when we have more computing resources, and this is like a production website, of course, we'll have a lot more bandwidth to handle our traffic.
Okay, thank you so much. So the next question is, what physics stands behind the waves coming from the earthquake to the ionosphere? What is this wave?
Leo, would you like to take that?
I can take that. Yeah, thank you. Excellent question. This is an atmospheric wave. Essentially, this is sound that is low frequency. For example, if you can show that slide, Siddharth, with the little schematic, please. That would be useful. Thank you. For example, a seismic wave might shake the ground the way a drum would oscillate, and this would create sound, just very low frequency. It will propagate up to the ionosphere and will displace the electrons there. And this displacement of electrons that, in fact, is measured by the technique that we're talking about.
So
Importantly, this is a mechanical wave and not a radio wave, as
exactly
Mark pointed out.
right.
Pressure. You may well mention the pressure waves and the gravity waves. There are two types of pressure waves and gravity waves.
If we want to go more into details, this sound can take different forms. Indeed,
Sure.
Tila. Excellent question. Excellent precision. Either the dynamics at play would be similar to sound, that is pressure wave, compression and decompression of a signal, but it can also be gravity wave, not to be confused with gravitational waves. Those gravity waves, instead of using pressure as a restoring force, they use buoyancy, because essentially they are very low frequency wave, and so low frequency that the wavelength actually displace enormous amounts of air that eventually will return to flotation where they used to be. So this is another physical aspect, maybe less common and a bit more difficult to understand, perhaps. I'm happy to explain a bit more, but yeah.
Yeah.
Thank you, Sid.
Thank you very much. Okay, so the next question is, it is good that we now have all of these data, but have we the system to calculate all of that to anticipate the disaster before it happened? And if we, I guess, and whether or not, I guess calculating, the question is, I'm going to interpret the question. How much time do we have before an earthquake, tsunami, and volcano?
So, to the best of our knowledge, there is no scientifically credible way to predict that an earthquake is going to happen. So we don't have any warning that an earthquake is going to happen. However, tsunamis typically travel on the open ocean at the speed of an airliner, right? So say an earthquake happens somewhere in Japan, and you're a person in Hawaii, it takes several hours for that wave to reach Hawaii from Japan, right? But it's only taking 7 to 40 minutes for that wave to actually reach the ionosphere, and then say another 3 to 4 minutes for us to process the data and get it to you. And so that's kind of the event where, if things are moving slowly, uh, and the signal is moving faster than the actual event, you can get several hours of early warning using this. The other case is also, say, volcanic eruptions, right? So one of so the area of ionospheric disturbances from volcanic eruptions is actually very new. It has not been studied very carefully. And we are sort of in the process of exploring that area a little bit more. But when volcanic eruptions happen, sometimes there will be smaller precursory eruptions that will lead to the main eruption. So in case of Tonga, there was a whole sequence of precursory eruptions that sort of increased the risk slowly. And so in that case, if you start picking up, say, TEC perturbations from smaller eruptions, and you start to see that it's happening very often, especially in areas, for instance, where a lot of these volcanoes in the Pacific, it's very hard to get there, and it's very hard to install ground-based sensors. But the GNSS receiver can see 1,200 kilometers away. And so if you're able to monitor these volcanoes that way, then you can have some warning that maybe there's an impending volcanic eruption. So earthquakes, no predictive capability that's scientifically credible, at least, and statistically credible, I would say. But with volcanoes and tsunamis, for instance, there is some potential here for predictive capacity.
Okay, thank you very much. I'm going to take one more question from the chat, then we're going to hop over to the Q&A for the extended Q&A session. Given the inclination of the GNSS satellites, 55 to 56 degrees, and the paucity of GNSS stations at high latitudes, does this degrade the high latitude observability of the ionosphere from GNSS data?
Attila, would you like to take that?
Yeah, that's a very good question. Certainly in the high latitudes, there's a lot more variability in the ionosphere, and that could be masking the signal. If a big earthquake happens near the Aleutian Islands, for instance, which is a fairly frequent event, there could be an issue with the noise level of the GNSS data. But careful examination of the data and cross-correlating data with other nearby stations could typically alleviate this impact. So we are actively looking at this. That's specifically a very interesting area of research, and we are paying actually a very close attention to that, an active area of research. Thank you.
Okay, thank you, Attila. So some of these may have been answered in the Q&A, and so I'm going to, all right, so the next question is with text answer. Did somebody want to add something to this, or are you ready for the next question?
Oh, we're ready.
Okay, perfect.
I was trying to address a number of questions online. I'm not sure how many I ended up answering. Many were coming in, so I was trying
Yes, there are quite a few. And so now I'm trying to sort through to see which ones you've answered. Okay. All right. So let's take this next question. Although much more challenging due to unpredictable mobility, lower TX power and RX capabilities, etc., would it be possible to use the GNSS signal from and to mobile devices? And now I'm seeing that you had answered that
Good.
within the chat.
Good.
So let's see here. The next question is, how is the integer number of ambiguity resolved?
So, so we actually, for this purpose, we don't actually need to resolve the integer ambiguity, because what we're looking at is TEC perturbations and not the absolute value of the TEC itself. So when you remove the DC offset, like that basically goes away, and then you're also differencing two separate phases, and so it's actually not something that ends up being a huge problem. So when we do see cycle slip jumps, we have a GNSS editor that one of our team members has who's credited on this presentation has created, and it is able to pick those cycle slips and able to address them and remove them from the individual phase arcs.
Okay, thank you very much. Okay, moving to the next questions. Are the GNSS observations processed using the PPP approach?
No.
Yeah, Attila, you want to go
Yes,
first?
we are not using precise point positioning in this case. So we are not solving for XYZ coordinates and clocks and orbits and other parameters. This is simply using the L1 and L2 phases, as Siddharth mentioned, forming the so-called ionospheric observable, the ionospheric combination. So we don't need to do PPP or ambiguity resolution or high-end computational techniques that most people use for other purposes. Yeah.
Okay, thank you very much. Okay, so the next question is, and I see that there is I think it would be worth answering this question. There have been instances where historical ionospheric data from the JPL has been missing, and I've been able to use data from the ESA instead. Is there a backup alternative for the real-time Guardian system?
I thought I answered this question by asking whether this was a post-process,
Archived or
archive,
real-time, yes.
archived or real time, because we are dealing with real time data here, but we are archiving the real time data, and we are uploading the real time data thanks to Leo to NASA's portal CDDIS. So any data that you see here going forward will be directly sent to NASA's CDDIS for science purposes. So if we may have missed some other data source, some Rhinex file may be missing from CDDIS, we would be happy to work with you. We could certainly reach back and retrieve some of our old data from this GDGPS network as well.
I would like to,
Leo,
add a bit to that, because I saw by chance in the chat someone asking a related question to me privately, so it didn't show.
Okay.
Moha El Ayachi, to answer your question too. The question was for stations not connected to Guardian, could we use that? And I feel like this could be answered by some of the prospect that we have, which is to have, we'll see if we can make that happen, but to have a software that can be used by individual station owners, not necessarily linked to the Guardian system for one, but also a network. And this is particularly useful for stations or systems that are in remote locations. For example, Tonga, unfortunately, during the eruption, was cut off from the entire global internet. And to have the software running on the island with a single station, not necessarily connected to anything else, would be something we are looking to explore. So that could also, I feel like, answer that question about US government funding and availability of the system itself.
Okay, thank you so much, Leo. So the next question is, and what I'll do is I'll take the next several questions in the Q&A, and then we'll hop back up to the chat because I do see additional questions there as well. And we'll go as far as we can until 3:15. What about the sensitivity of Guardian detector of ionospheric events? Does it depend on the receiver and on the GNSS constellation type?
Yes, the short answer is yes. If you recall, during the demo, there were some stations that were slightly high noise, and there were some stations that were low noise. That depends on a lot of things. It depends on the location of the station. So for instance, like a polar station tends to have higher noise than a mid-latitude station, right? But it also depends on the receiver quality. So sometimes if the receiver loses lock pretty frequently or has cycle slips, etc., typically the data that we get from the GDGPS network is actually very high quality. I think the challenge is that because we're doing ionospheric combination, we need two separate phases, both to be really clean because you're differencing them, right? So if you do precise point positioning, typically, like you can work with the L1 phase being very clean, for instance. But here, sometimes what will happen is that one of the phases will be fine, the other one will be kind of noisy, and that creates noise in the system. So in a clean station, so Goldstone, for instance, which I showed you, the noise level is typically like about 0.05, 0.03 to 0.05 TEC units, so under 0.05 TEC units. And so those stations tend to be very, very sensitive. Then again, if you're looking at a time when there's like a big solar storm happening, that noise level tends to go up and down. And so the sensitivity shifts as a function of time of day, as a seasonal variability, solar activity variability. So there's like a lot of receiver, but also environmental influence factors on the sensitivity. I don't know if Attila or Leo, you want to add anything to that?
It's pretty clear to me.
Yeah.
Yeah.
Yeah, I would just underline the quality of the data is extremely important, especially because smaller quakes generate smaller signal. And I mentioned that in one of my responses that typically 6.8 magnitude 6.8 is a cutoff. I think one of our dear colleagues established that. She's online, and this is something that we are paying very close attention to. So very clean data is absolutely a must. And there is also a difference among constellations. Different constellations have different noise levels, so we are taking that into account as well. But overall, so we have like up to 50, 60 measurements from any one time. So we have quite a bit of data strengths these days, especially at well-established locations with high-end GNSS receivers.
I feel like this links also nicely to another question by an attendee earlier in the talk about using cell phone receivers. The noise level there would be much higher, but it's also something that we are exploring for crowdsourcing data.
If I may add to that, there have been a number of presentations lately looking at dual frequency phones for ionospheric research, and the results have been sobering. So the data is quite noisy at this time. So we are looking for new ways of processing the data and maybe new signals coming along. So this is still an issue. Low-end GNSS receivers would not be able to get that kind of low signal-to-noise ratio that we need for this type of research. That might change over time. Certainly, that receiver technology will continue improving, but right now we are focusing on this high-end GDGPS network using the best possible data quality globally.
Well, thank you very much, Attila, and also thank you, Leo. So the next question is, how can we know that this much of and I'm not sure if this is pronounced TEC or tech, disturbance is considered, this is not my field, is considered as the result of a tsunami or earthquake, and that this amount of variation is natural and safe?
Yeah, so this is, I mean, strikes at the kind of heart of the problem, right? Like what is a real thing that is worth issuing a warning for? And I guess inconveniently, the answer is it depends, right? It depends on what the event is. It depends on what the ionosphere is doing at the time of the event. It depends on the quality of your data. But I think the real advantage here is having a large number of observers, right? So the way we figure out something is real is when a large number of people, so if I like to think of it as a large number of people lying independently, right? If everyone lies independently, but the lies match up, it's likely the truth, right? So that's why having a large number of stations, having a large number of constellations is really, really valuable in this case, because you have redundancy. If signal fails or like is noisy on one link, you have like 10 other links to look at. And so a lot of our automated detection and inversion attribution work really goes into examining this kind of stuff, where like we let the neural network learn what normal looks like, and we use as much data as possible that's as clean as possible for it to learn. And even then, it flags anomalies, right? But then the next check is it flagging anomalies only on a single link, or is it flagging anomalies on like a large number of links that are all spatially close to each other, and they're all sort of doing it in phase? The frequency of the perturbation is in the right range for something that's, say, generated by a tsunami, for instance, right? So you have all these checks, and even after that, right, you produce essentially a short list for an expert to look at. And so you're never going to be relying entirely on a computer to tell you, hey, something's going on. But the computer can definitely help you shortlist the amount of stuff you have to comb through to reach that conclusion. So the question you're asking is like strikes at the very heart of this entire area, and it's very well taken. And it's just it's a work in progress. It's research. Yeah.
And with that, there are always, of course, complementary techniques that come in. So if we are unsure about an event, that there are also other techniques and buoy systems, tide gauges, and other signals that are completely independent of the system. And they are so when it comes to decision making, this is where the experts come in and look at all the data at their disposal to issue warnings and additional measures to put in place.
Okay, well, thank you very much. And so we probably have time potentially for 2 more questions. And so I am back up in the chat. There are a few that have not been answered as of yet. Is the time of day or day-night a parameter into the classifier? For example, the feed in the day-night as an input parameter into the classifier.
So the classifier, I should be clear about this, is essentially a prototype right now. It's not something that's running actively on the stream. So we prototyped it for the Turkey earthquake. I don't believe the time of day. Leo, can you correct me if I'm wrong here? I don't believe the time of day was an input into the, and it's also not a classifier. It's more an anomaly identifier. So it's not telling us why the anomaly is happening. It's just saying an anomaly is happening. And so even though we don't explicitly specify uh, time of day, it's sort of, because it's ingesting daytime data in the training set, it sort of knows it's included within the range of variability for normal, right? So it's not explicitly specified, but it is something that implicitly gets ingested in there, and so it does show up in that test case with the Turkey earthquake sequence. So that's not something we run. It's not a running engine right now. It's an active area of research, and so we found some good results with a prototype event. But of course, there's more work to be done.
Okay, well, thank you. With that, we have reached the end of our extended Q&A. So at this point, I do want to let all of our remaining participants know that I will be sending the Q&A log to our Q&A panelists, as well as to our speaker, and they will be able to follow up with you offline, along with the chat log. So if we didn't get to your question, my apologies. There were quite a few. I'm sure there were probably over 100 questions. And so thanks so much at this point to our speaker and our Q&A panelists for joining us this afternoon. Thanks to all of you for joining us as well. And then the final note is that I will send a link to the recording and to the into the presentation slide deck within a few weeks, excuse me, a few days of completion here. Okay, so hopefully by Friday. So thanks so much, everybody. We'll leave the virtual meeting space opened, and we will close out of the audio at this point.
Thank you, Jennifer. Thank you, everyone, for joining us.
All right, thanks so much.
Thank you very much.
All
Thank
right.
you.
You.